Greeting fellow learners. Welcome back to another video where I'll be covering the bolts and screws of the topic nuclear quantum physics. Let's get cracking, shall we? Kicking off the learning experience with an interesting underlying concept, I'll begin talking about Rutherford's gold experiment as displayed in the image. There are countless online versions of this apparatus, so feel free to immerse yourself in those available. Let's go over the function of each part contributing to the entire experiment. Oh, here it is. Okay. The experiment begins with a lead container featuring a hole at the front, positioned to face a sheet of gold foil. Over here. Okay. This setup allows a collimated beam of particles to travel perpendicularly towards the gold foil. This experiment is conducted within an evacuated chamber to prevent alpha particles from interacting with air molecules, as they are highly ionizing and could be deflected or absorbed before reaching the target. Gold foil is used as the primary material in this investigation due to its ability to reveal the intricate structure of atoms. Additionally, a detector is placed around the setup to capture alpha particles from all directions. It records both the angle of deflection and the number of particles deflected at each angle. In summary, this experiment involves firing a beam of high-energy alpha particles at a thin gold foil. While most particles pass straight through, some are deflected at small angles, and a few are deflected at much larger angles. The most surprising observation was that some of the alpha particles were deflected directly back towards the source, a result that astonished Rutherford and his team. Okay. Now, these are the key observations made from Rutherford's gold experiment. The majority of alpha particles pass straight through the foil, indicating that atoms are mostly made of space. Some of the alpha particles were deflected at small angles, 10 degrees or less, suggesting that the presence of a positively charged nucleus at the atom center. A very small number of particles were deflected at greater than 90 degrees, revealing that the nucleus is both small and densely packed with positive charge. Alright, now, let's move on to nuclear notations. These are very simple. If you've done physics, then you probably know all of these already by now. The characterization of the nucleus. Over here, X represents the chemical symbol of the elements, A is the mass number, Z is the atomic number, as seen in this example where carbon has a mass number of 12 and atomic number of 6. Alright. Mass number can be calculated by the total number of protons or electrons plus neutrons in the nucleus. Now, the reason why I say protons or electrons is because number of protons is equal to number of electrons. So let's say a question says that the number of protons is, in this case, for a carbon atom, 6. Then number of electrons would be 6 as well. The atomic number is the number of protons or electrons in the nucleus defining the element. And this determines the identity of the element. And you probably have heard of this statement already in chemistry. Now, the formula that is most typically used is A is equal to Z plus N, as in mass number is equal to atomic number plus number of neutrons, which is represented by N. And if you rearrange the formula, you can calculate the number of neutrons as portrayed in this formula. Alright, in a neutral atom, atomic number Z also equals the number of electrons.